Welcome to Research Digest podcast. In this episode, we'll talk mostly about environmental chemistry and how computational approaches like molecular simulations can be used to solve some of the major questions in the field. But first, let me introduce you with our guest today. I'm happy to have Dr. Mirza Galib with me. Dr. Galib is currently working as an assistant professor at Howard University in the United States. Galib bhai, welcome.
But no, thank you so much. It's my pleasure.
Okay, so let's start our discussion with environment. Okay, everybody is so concerned with the environment, and you published a really interesting and important paper in 2021 in Science Journal. In this paper, you talked about the dinitrogen pentoxide, which is an important atmospheric compound that acts as a major nighttime sink or as a reservoir for nitrogen oxides. The mechanism of the uptake and hydrolysis of dinitrogen pentoxide from atmosphere was kind of difficult to verify. But in this paper, you proposed an inverse mechanism and proved it by molecular simulations. Right. So, in simple terms, please explain what you did and what were your major findings.
Okay, thank you. I mean, even though this work is related to environmental chemistry, but our focus was basically from molecular simulations because I'm a computational chemist.
Right.
So what we do in computational chemistry that if you are experimentalist, go to the lab and try to understand a chemical reactions. You want to see that
Yeah.
how the two reactants come close together, right? And they
Yeah.
react and they overcome an energy barrier and go to the products. So that's
Mm.
the general chemical reactions. And then we ask two different questions to understand a chemical reaction. First question is that how much energy you need to move from the reactant side to the product side. Is it
Right.
easy to move there? Or, right, if I compare the energy of the reactant and the product, which one is higher, which one is lower, that will give you the thermodynamic probability that where my reaction will go. So that's the first question, the energetics. Then the second question is we try to understand that how much time it will take from going from reactant to the product. So
Mm.
that's known as the rate of the chemical reactions.
Right.
So you need to just set up a lab and then do that experiment and use some experimentation technique to find out the thermodynamics energy. We call that free energy and the rate of the chemical reaction. So that is if you're an experimentalist, you do that. So now let's say that I'm not an experimentalist, I'm a theorist and computational chemist, and asking the same question that can we calculate that? That what will be the energy barrier of a chemical reactions, or what will be the rate of a chemical reactions, or either to write down some complicated math to do that number, or right, can we simulate the system? Because when I'm saying that this is a chemical reactions, I exactly know what atoms and molecules are there, right? So
Yeah,
for
we know
example,
the properties of those compounds and
yeah, exactly. We know how many electrons and protons are there. So for example, I'm interested into N2O5, so I know exactly that molecules. And I'm talking about an aerosol particle. So these are tiny, small water droplets in the atmosphere, right? And
mm,
you might have other chemicals into that. So that is actually water, but not the pure bulk water. So that will be just some droplet size water, right? Nanometers to micrometer size. So if I exactly know what is in there, then I can develop the simulation protocol. Now, what is the problem? The most important problem in the simulation community is that when you have these atoms that come together, make the chemical bonds, and that make you a molecule, and when one molecule comes to the other molecule, so they have some interaction, right? The
mhm,
electron cloud comes very close to each other, and then the nucleus in one side interact with the electron on the other side, and the electron on the other side interact with the nucleus.
right.
Now, how do you model this interaction, right? What is the formula? Can you write an equation that will tell us what will be the interaction between an oxygen and an oxygen atom, or the interaction between a nitrogen and nitrogen atom? So that's a very, very complicated question. So in molecular simulation, we have a couple of different way we do that. Right. One thing is classical simulation. So we just make down that the interaction is two body, the only two particle interact at a time. And then I sum over all the two body interactions. But in real life, the interactions are many body. There might be three body interactions, four body interactions, five body interactions. So how do you compute that? So one way we do that we do quantum mechanics, that you don't write down an equation rather than write quantum mechanics is completely different. You write down a call a simple but complicated Schrodinger equation, and you need to solve that Schrodinger equation. So now there are many different approximation. One approximation is called density functional theory.
Okay.
Right, a lot of experimentalists also know that because this DFT is very popular, and I
Mm-hmm.
think people who invented DFT, they got Nobel Prize. So this is so widely used in
Yeah.
the simulation community. So you can use this density functional theory, that is one kind of quantum chemistry, to solve the interaction between the atoms and molecules. And if you know what is the interactions between the atoms and molecule, you actually can simulate a chemical reactions and calculate the energy and the rate of the chemical reactions. So that's the background that why we
Okay.
use molecular simulation to
Okay.
understand.
Here, I have a small question.
Yeah, sure.
So, in the many body interactions you mean, did you mean the different atoms or different compounds?
No,
This.
but you can think about from an atomic perspective, different
Okay.
atoms. Yeah. So I think that that will be the right way, because we know that, right? What is the difference between atoms and
Mm.
molecules? Molecules has the chemical bond inside, right? And when you
Right.
have one molecule to other molecule, their bonding is not chemical, right?
Mhm.
Like a strong covalent and ionic bond. It's not like that. They're far away from each other, and they will have some dispersion forces. Now, right, it is just a function of distance,
Okay.
right? Because this chemical bond is a hypothetical imagination. We think there is a bond, but there is no rod type bonding in there,
No,
right?
no.
It's actually just the atoms come closer, they interact with each
There
other.
is electron density and maybe some overlapping regions and those
Yeah,
things.
exactly. So if the electron cloud on side comes to close to the other side, they will overlap, right? And
Yeah.
that interaction is just very hard to model those from a computational point of view. So if we have a reasonable computational protocol, then we actually can calculate the kinetics of those chemical reactions. So that's the focus where I'm coming from the
Okay.
molecular simulation. Now let's go to the problem that we tackled in there. So
Mhm.
how it is related to environment. So we have the aerosol particle, right, in the atmosphere. This aerosol particle are primarily coming from ocean water, right? So you have the wind that takes some of the water out from ocean
Mhm.
to the atmosphere, and then they become very tiny, small, right, nanometer size particle. I think, right, 10 to 100 nanometer up to micron size they can be. And then these aerosol particles just move around our atmosphere, the lower atmosphere. And there are many different gases into the atmosphere. These gases can enter into those aerosol particles. Then we
Okay.
have the dust, right, that's in the atmosphere. So this
Mhm.
particle, right, can accumulate on top of a dust and make it very, very complex. Now, how much aerosol particle you have and what kind of properties you have, that dictate the air quality in many perspective. Okay, so
Mhm.
right. So sometimes, for example, you have very foggy environment, right? If you have, right, more particles in the atmosphere, that create more aerosol, and that may make you the more foggy characteristics.
Right.
And the air
Right.
that you inhale.
Yeah, right. Air quality is a very critical issue, and
Yeah, exactly. So air quality is a really, really critical
uh,
issue. So
we don't see most of the things that are present in those aerosols. Uh, Maybe fog we can see, but we don't see most of the things like components in
yeah,
that.
exactly. They're so small and tiny.
Yeah.
You can see that, right? But the right, when you inhale
Hmm.
the air, it's always right. Those
Okay.
things have a very high impact, right, on the air.
Hmm.
So atmospheric scientist has a huge interest to model the air quality. That, right, if I know that how many particulates matter you have in the air, what kind of gases are there, what is the temperature, what is the wind flow,
Hmm.
can we model that, right? Is the air quality going to good or bad, right? What will
Right.
happen in the morning, what will happen in the evening, what will happen down the road, and then
Mm-hmm.
they try to improve the air quality. So that's where this motivation is coming from. And then if you really want to understand this air quality and model the things, then you need to understand what happening inside those tiny small water droplets or aerosol particle. So
Right.
that's where this motivation is coming from. So the
Mm-hmm.
specific problem that I was interested into, that you have a small water droplet, and let's say some gas molecule that we have in the atmosphere that come close contact with the aerosol particle. And what will happen? They will react with the aerosol particle, right?
Mm-hmm.
And this
Yeah.
reaction is a heterogeneous process because I have a liquid in one side, and in the another side I have just a gas molecule. So you have a gas liquid interface. So
Mm-hmm.
this process is very complex because it involves a couple of many different steps. So for example, the first step, this gas molecule will come close to the contact of the surface. So they can hit the surface, then get stuck here, or they can bounce back. So both of the things happening depending on the incoming, the velocity of the incoming gas molecules. So that will be the first
Right.
step. And let's say that a fraction of those molecule get absorbed at the surface of the aerosol particle.
Okay.
Now that particle can stay at the surface for some times, or they can move inside the aerosol particle. So this aerosol particle means, I'm thinking that you have a bubble, right? A small water droplet. Now
Mm-hmm.
this is all water molecules in there, and then it comes to the surface. Then slowly it go inside the aerosol particle. Now, when it goes aerosol inside the aerosol particle, this is solvation, right? That I have a
Yeah.
gas getting solvated into the water molecule. But interestingly, this process can be more complex, that that gas molecule can react with water. So for example, in our case, we are interested into the N2O5, dinitrogen pentoxide, that reacts with water. And first, it can dissociate into NO3 minus and NO2 plus. And then both of them can react with further water molecule and can form nitric acid, HNO3. So that will make the aerosol particle acidic, right?
Mm-hmm.
So this nitric acid can be undissociated nitric acid, or they can dissociate and give you H plus and NO3 minus. So a lot of chemical reaction can happen in there, right? So
Mm-hmm.
now, one thing that this chemical reaction can happen at the surface, or this chemical reaction happen inside the bulk,
Right.
right? So this will be a composition of many different process, right? The first
Mm-hmm.
hitting the wall of the aerosol particle, then a fraction of that, right, going back, and other get stacked there, and then it can either react at the surface, or can diffuse inside the bulk of the aerosol particle, and it can react inside the bulk of the aerosol particle. And now, if you try to understand that how much N2O5 from the atmosphere will enter into an aerosol particle, and what is the ratio? Let us say I have, right, some N2O5 molecules. Is this 50% of N2O5 enter into the aerosol and convert into the nitric acid, or this 20%, or
Mm-hmm.
this 30%, or this 70%? So that's a very crucial question, because if you don't know that what kind of chemical reaction is happening, we cannot model that what is the properties of this aerosol particle, what will be their lifetime, how long they will be in the atmosphere, right? Are they going to be acidic, are they going to be basic? So you
Right.
don't, right, if you don't know those details, you don't know anything about the atmosphere.
Mm-hmm.
So people try to write down simplified equation to describe all of this process. So let's say I have, right, couple of many different process, each of them coupled with each other, and I'm trying to write down some simplified equation that can explain all of them. So you need to do two assumptions for that. One, you will ignore some of the part. Let's say that too many steps, I ignore some of the part, right, and just drop that out. That things become simple. The other thing is that you ignore the coupling terms, that if two of the steps become coupled to each other, then you have a, right, correlation term, and that correlation term is extremely difficult. So you can drop that correlation term. So what people conventionally does that they first they did not think that the reaction can happen at the interface at all. They think that the only reaction can happen that if you go inside the bulk, then the reaction happens.
Mm.
Right. So
Okay.
that was convention because interface they thinks okay, so this is just a very tiny little interface. It
And
might be
interface is very complicated.
yeah, exactly. Because our conventional knowledge about the interface is not that much. So
Mm.
that's why people think okay, there is no reaction in the interface. And then they write that if the reaction is very fast, then your diffusion and the reaction, those two can be coupled. But
Okay.
if the reaction is slow, then everything will be diffused inside the bulk. So they have the second assumption that, okay, let's say that reaction is extremely slow. So those are the two assumptions people made, and they build a model called resistor model and explain all the experimental data by that.
Okay.
Right. And one of the reasons they did that, that's simple. And another reason was that they did not know every single step. So it's very hard from experimental point of
Mm.
to measure the rate of these within inside an aerosol particle, because the diffusion and the rate of the reaction that comes in a couple term. If you do an experiment, they don't know how to decouple that. So
Mm.
that is the problem why they went through
So
this
so
model.
based on that model, it was believed that it is absorbed inside the bubble, and then subsequent hydrolysis takes place, right?
Yeah, exactly. So
Mm.
it is believed to mean, right, there's no rational for that. They just, right, there's a conventional knowledge. The people think that
Okay.
okay, no chemical reactions happen at the interface. So
Mhm.
there's this thing, interface is just a gateway that this gas molecule just enter into the interface, and then everything is the bulk. So
Okay.
that was their assumption. Now, from a theoretical point of view, right, it's easy to model all of those separately, because theory is theory. You don't have the experiment, right? You can actually, right, play around that I set up
Mm.
only interface, I set up only the bulk, I can look into the chemical reaction of the interface. But the problem is, right, that many body interaction, the level of physics that you have in there may be inaccurate. So you can get a rate, but the rate may be not the right number. It is off from the experiment by a very large uh, number, and you don't know how much off it is. So that's the problem of the theory side. So
Okay.
what we did, that we actually started with density functional theory. So that's a quantum
Mhm.
mechanical model. And then we borrowed some techniques from the contemporary machine learning to build a surrogate model of the density functional theory.
Okay.
Right. So all the data, so this is actually fitting the data. All the
Mm.
data will be coming from density functional theory, and then will fit to the machine learning model. And that will give me a surrogate model by which I can do the molecular dynamics simulation. But I can do it now much faster than the original DFT, and I can simulate
Mhm.
for longer time because it is faster now. And I can also tackle a larger simulation box size.
Right.
So
Using the surrogate models like the
yeah,
thing.
for the surrogate model, exactly. So
Okay.
one of the novelty that we have in this paper, that we have developed a surrogate model from density functional theory and machine learning. So the density functional theory is our parent model, and then we use the machine learning to develop the surrogate model.
Mhm.
Now we applied this surrogate model to actually compute the thermodynamics and kinetics for each of those steps. Right? We ask the question, okay, a gas molecule is hitting the surface. What is the percentage that it gets stuck? Then the
Mm.
question, reaction happening at the interface. If that happens at the interface, what is the rate of the reaction?
Right.
Then let's say that does it go to the Does it enter into the bulk? If
Mhm.
that, what is the diffusion rate? And then okay, the reaction happens at the bulk. How fast it happens there? So from a simulation point of view, we are able to calculate all of them. So our simulation is not exactly right, because still the density functional theory that we use is not accurate. So it's an approximation, but that gives more or less a qualitative understanding of what's happening. And
Okay.
from simulation, we made we actually discovered a couple of things. First, that the reactions happen at the interface and as well as in the bulk. So in both places. So the previous assumption that there is no reaction in the interface That's not right. So you actually need to replace the conventional model by
Hmm.
something where interfacial chemical reaction is there. That was the first thing. The second is that the reaction of the dissociation of N2O5, that's actually very fast. I mean, it's not a very slow process. So your diffusion and reaction is not very decoupled. So if you just actually apply
Hmm.
decouple assumption, that doesn't work, right? In many cases, it just
Okay.
within hundreds of picosecond time scale, the
Hmm.
reaction happens. So from that point of view, we just concluded that if you try to understand that how an atmospheric gas particle enter into the aerosol and react, you need to be very careful that you can't ignore the interfacial reactions at all. And sometimes the way you simplify the model, you may not be able to simplify. So that's the bottom line that we
Okay.
conclude from that pair. So I think the paper is significant because applying this machine learning surrogate model for such complicated system, that's something contemporary. I mean, a lot of other people are doing that, but this is also significant work that shows the power and the efficiency of those surrogate DFT model. So that's one thing. The second thing is just questioning the resistor model, because a lot of experimentalists in that atmospheric chemistry using those resistor model. And
Hmm.
this paper actually questions that you need to think about the interfacial reactions. Interface is important.
Yeah, interface is important. Okay, let me briefly show you another article that your group published in the next year in Nature Communication Journal, where you quantified the thermodynamics and kinetics of solvation and absorption of uh, N2O5 in water using same molecular dynamic simulations. So just briefly tell us about the major updates in that next
So that
paper.
that work is actually a continuation of the first work that we
Right,
talked
right.
about. And so the first work, I did that when I was a postdoc with David
Mm-hmm.
Lieber at UC Berkeley. So at the same time, we were connected with a couple of other experimental groups and theory group. So this paper is a collaboration with another theory group at UC San Diego.
Okay.
So what we did, that in the first paper we asked the question that the mechanisms how this gas molecule enter the
Mm-hmm.
atmospheric particle, that's complex, and you need to consider all those steps independently and individually rather than simplifying the process. So
Yeah.
that was our contribution from the first paper. Now we ask the question that since we now know the mechanisms much better, uh,
Mm-hmm.
can we compute them more accurately? So that was the question, right? That can you
Yeah.
compute it more accurately? So in this paper, we developed another theoretical model, and this is not DFT. So it's a very high level quantum calculations that is much more accurate than our previous model.
Okay.
But one of the limitation of that model was that it cannot understand a chemical reaction. It can understand water, it can understand solvation, it can understand the diffusion, but it cannot understand a chemical reaction, because during a chemical reaction, a bond is broken, right? So it's very simple, right? I have a nitrogen and oxygen bond, and that bond is broken. So it looks like very simple, but when we go for modeling, it's extremely difficult to model that. So the method we used in here is much more accurate than our previous DFT method, but the limitation of that method that it cannot model a chemical reaction. So what we did, let's say that let's use this model just to understand the solvation. That if I have a gas molecule coming to the interface and I assume there is no reaction, then it will passing through the bulk, right? And I can ask that what is the percentage that will go to the interface and what is the percentage that will go to the bulk, right?
Mm-hmm.
That will depend on their energy. If the energy on the both side is same, that will be 50-50, right? If the energy on the bulk is right here and that one is here, then you'll see that 80% goes to the bulk, 20% at the interface.
Mm-hmm.
So I can use that more accurate model to get this distribution, that how much is going to the bulk and how much is going to the interface, right?
Right.
There's an energy barrier going from the interface to,
Mm-hmm.
so we computed that from there. And now, right, from the experiment, we know some other parts. So experiment doesn't have the reaction rate part, right? They have a combined term, that's right, the diffusion and the reaction, those two get right sliced into one term into their experimental setup.
Mm-hmm.
So we have the experimental values, and now we have the solvation. So we can assume, right, the reaction rate at bulk and at the interface, and see that what value best fit to reproduce
Right.
the data.
Best
So
fit the experimental data.
it's a
Okay.
kind of clever way that, right, I have one piece into the experiment, I have one piece into the theory does not have all the pieces that I need, and experiment cannot explain all the pieces I need. I'm just combining those two, and I have one unknown, right? That unknown will be the rate of the chemical reaction.
Mhm.
So we assume, let's say I have a bulk and I have the interface. Now from the previous calculation, we have a general idea that where the reaction happens fast, right?
Very
uh,
fast. Yeah.
bulk is much more faster than the interface. So we can assume, let's say the reaction is 5 times faster, 10 times faster. And we can put those assumptions into there and see that which fit can give you the experimental data. So that's why in that paper we have a bright better estimate of the reaction rate. So now this is one interesting thing, that this second paper, that paper actually have a better understanding of the rate constant, better estimate of the rate constant. But the first paper went through a better journal, because that is the first paper we addressed the question, and this is the first time you're challenging that, okay, the reaction can happen at the interface. But the estimated rate that we got in paper, right, that's not exactly right. The second paper get the better rate, but the second paper does not go to the better journal because it's a follow-up paper. So it's happening.
Yeah, yeah, yeah. That happens. Yeah. So thank you for explaining in very simple terms. I hope our audience will find it interesting. So now let's talk about your current research focus. Now you have your own group at Howard University, and you are working on different aspects using these computational simulation models and trying to understand the complex interactions in the environment. And tell us more about that. What are
So
you trying?
I'm still right more or less in the similar area, that our interest in that how we can use this molecular simulation tools to understand complicated system where you have chemical
Mhm.
reactions, solvation, and this can be related to, right, air-water interface that's relevant to the environmental chemistry, or it can be solid-liquid interface that's more relevant to the battery materials, the
Mhm.
electrochemical devices. And we're also interested into catalysis, that how we can develop the better catalyst. So what I'm doing primarily, right, going back to that surrogate model, right, that those that the N205 paper, that science paper, that clearly shows that if we can train a surrogate model by the machine learning from the DFT data, that
Mhm.
makes our life much more easier, and we can tackle more complicated questions, can answer a lot of complex chemical phenomena that happening around us. However, this machine learning model is very right, data hungry, right? Where you get those data from, that's a very big question.
Yeah.
Also, right, what kind of physics you include into the machine learning model, that's also important for us. So this is exactly the same model that the computer science guy used, right, to find out whether this is a cat or a dog, right? You train a lot of data and ask a new image and
Right.
asking, is it a cat or is it a dog?
Mhm.
So it's exactly the same principle, but since this is a chemical system, you have to tailor it by yourself, right? So my current project are focusing on that, right? How we can develop a better machine learning model from the DFT data for liquid system. So I'm interested into water, interested into putting water to the air water interface, and right, any other liquids. So for example, one liquid I'm interested into called ionic liquids. So ionic liquids are
Okay.
just cations and anions. there's nothing else, so no water. So it just some organic cations, organic anions with some cations, and those are room temperature liquid. So that means, right, their melting point is lower than, let's say, 100 degrees Celsius. So if even the room temperature 30 or 40 degrees Celsius, they're liquid. But generally, right, if you think about, let's say, sodium chloride is the salt, right, that we,
Mm-hmm.
that's table salt, but this is solid in the room temperature. If you want to melt sodium chloride and making liquid sodium chloride, then you need to heat that a lot. I think it's more than 800 degrees Celsius. I exactly forgot,
Yeah, yeah.
but it's very, very high, right? You need to, right, go to very high temperature to make that liquid. But these ionic liquids, those are, right, the anions are much more larger, and they're not symmetric. They're not round that you can peg them. So since they're not packing very well, that frustration make them liquid at very lower temperature. So you can be in lower temperature, but it's liquid, not a solid.
Mm.
And you can use that into making the battery. So this is called the concentrated electrolyte. So when you make a battery, you have a solid interface, and then you have a liquid interface, right? So two solid interface, anode and cathode on the both sides, and the liquid interface
Mm-hmm.
in between. So that's the solid liquid interface. A lot of things happening into there. So now if we want to simulate that, right, DFT is a very good method to do that. But the problem is that density functional theory is computationally expensive. What do we mean? That if you want to run 1 nanosecond dynamics, that what happened in 1 nanosecond, it takes a lot of computer power, right? You need to run that simulation, right, for a month or maybe more than that. So that's why we are interested to develop the surrogate model from the machine learning that will speed up the simulation,
More efficient models.
a more efficient model. So in not in terms of accuracy, because if I fit to the density functional theory data, then my model will be as accurate as the density functional theory, not more than that. But it will make the simulation faster, so that I can model long time dynamics, and I can match to the experimental observable. Because experimentally, time is not an issue, right? Because
Mm.
you can measure for longer times. But when you do the simulation, then you have to do each step at a time, right? You're in here, then give a jump, give a jump, give a jump, so you move that slow.
So, is there any way to include experimental data to train your models?
No, generally not, because,
Mm-hmm.
right, in some machine learning, so I'm doing in a different way. So in a machine learning model, let's say you pick some experimental properties, and you know what is the material in here, and you are teaching this model the relationship between the structure to the experimental properties. So that's one
Mm-hmm.
way you can do that. But my interest is different, that I want to do a molecular dynamics simulation where I'll put all the atoms in a box, and we'll tell the system this is the interaction between the atoms, and then we'll ask the system to model that at a different time what will happen in there. So this is actually the Newton's equation, that if you know the velocity at the beginning and the position at the beginning, then you can just move the dynamics, that what will be the next step, what will be the next step, and what will be the next step. But these, at every step, when I calculate this interaction, that becomes very, very costly. It takes a lot of time to compute that. That's why the density functional theory is slow. Now, with the surrogate model, we want to make the system faster, so that I can simulate a long time dynamics, and answer some interesting experimental question
Mm-hmm.
in there. So that's my goal. So we currently, right, working to develop more efficient machine learning model. So the question we ask, that how do you generate the data, right?
Right.
Right, and how much data will be uh, a sufficient amount of data? At what point we understand that my surrogate model is working well, right? And if it doesn't, right, work well, what will be the way to overcome?
Mm.
So those are the questions that we are now doing. And then what I'll do with this surrogate model. So one specific question that I'll be doing is, right, I will be interested into these concentrated electrolytes, and then putting that into the battery material and try to understand that if you apply a voltage, right? Because in the battery you charge and discharge. So I have a solid liquid interface, and I want to see that if you apply the voltage, now, right, how these concentrated electrolytes behave.
Mm.
And from that behavior, we'll try to understand that if these specific concentrated electrolyte that I'm using, is that a good electrolyte for a better battery? That's the question. So now, why this is important? Because ionic liquids has an interesting thing that you have a many different combinations. So let's say I have 10 different anions and 10 different cations, and I can write cross match them. So that means I have many options in there, right?
Yeah.
And then let's say I mix two anion with two cation, then you have, right, the binary mixture. So it's exponentially becomes so if I have a question that I have 50 cation and 50 anion, that how many mixtures I can make, this is
So
actually
many.
in so many number of options, right? Now the
Mm-hmm.
question is that which of them is the best for a better material. So it's
Right.
actually picking the most efficient candidate electrolytes for the battery. Now, if you're an experimentalist and go to the lab, then you have to synthesize all of them separately, right? So let's say I have 1,000 candidate. Now you have to synthesize all the thousands by yourself, right? And
Mm-hmm.
test that in the battery material and see that which one is working or not. Now, this is, I mean, very tough job because it's need
Yeah.
a lot of work
And waste of money.
and waste of money and time. So
Time.
there are two ways that people try to solve this question. One, from experimental point of view, that they set up, they call it robotic way of synthesizing, that
Mm.
you will just make some robots, they can synthesize thousands and thousands sample quick, so that you don't need the human hour to do that. So that is one way people solve this. Another way, okay, that I'll not synthesize them, I'll not test them in the experiment, I'll do some theory, I'll do some calculations, I'll do some simulation at the first.
Mm.
And that calculation will give me a subset of those thousands of structure, and they will tell, okay, this 10 look the most promising. So
Right.
go to the lab and experiment and just do those 10.
Yeah.
That's fine, right? And if you are really right, if the simulation works the best, then you can pick the most promising one from the simulation and just tell the experimentalist, okay, I know that this will work. Just test it. But
Yeah.
I mean, simulation is not yet there. We cannot exactly pick the best one. But till now, the
At
way
least you can predict some of them.
we can
That.
give some guiding
Mm.
principles, and we can pick some subset from there, right? We can see, okay, this 100 might be the better among those thousands, so now test those 100. Or
Okay.
sometimes we can give a guiding principle, okay, if you just mix with a small cation with a large anion, maybe that better. Or if you use this anion, that will break down under the applied voltage, and that will not be a good electrolytes.
Mm.
So this is how we are using. So that's the one thing. The another project this I'm working is, there's a very common reaction is the nitrogen and hydrogen react with each other and make ammonia. And
Yeah.
this ammonia is, right, very crucial for the fertilizer production,
Mm.
right? So this is a very powerful reaction, right. I think
Yeah.
more 80-90% of the global fertilizer is coming from this chemical reaction. Now if you do the nitrogen and hydrogen reaction, right, to form the ammonia, you need to apply a very high temperature and pressure, because the reaction has a very high energy bar. So
Yeah.
nitrogen is triple bonded, right? You have a one nitrogen with one nitrogen, and this is triple bonded. So if you want to react with hydrogen, you need to break the triple bond. So that's require a lot of energy.
Mm.
Now, one way
It
you
was a
can,
revolution when it was a revolutionary experiment when it happened first time.
yes, I mean,
Because nitrogen and oxygen are all over the air, like in the air it's there, but it's not becoming ammonia easily.
yeah. So because, right, you have to overcome that energy barrier. So that need, right, you need to, right, supply some discharge of current or something like that, right? But I
Yeah.
mean, this reaction actually changed the global economy, right?
Right.
Because when we, right, when human, right, were able to produce this artificial fertilizer, that's contributed to the production of the agriculture a lot, right? Right, we have a prediction at some point that the way the global population is rising, we cannot right increase the agriculture production, and that will create a food scarcity, right?
Yeah.
That was the theory people thought, but then this scientific development actually changed the whole scenario. So now most of the ammonia production that now happen, they use a catalyst
Mm-hmm.
and a high temperature. So that's how they do. So right, some of the transition metal catalyst they use, iron is also a good catalyst for that, and then you increase the temperature.
Mm-hmm.
That's the thermal way. Now people are thinking that can we do that in an electrochemical way? That right, like a battery setup, I'll have a cathode and anode, right,
Mm-hmm.
and I'll have nitrogen and hydrogen in there, and if I apply the voltage, right, with that voltage they will react, and there will be a catalyst there too. So the electrochemical way will be much more right green way. That's
Mm-hmm.
one thing. The other thing they're dreaming that if you can develop in an electrochemical way, then you actually can make a small cell by which you can produce the fertilizer wherever you want. So it will be just a small device, right? You can take the nitrogen and then hydrogen. So you can have a water, split that, get the hydrogen from there. Nitrogen in the atmosphere, right? Somehow you take the nitrogen from the atmosphere, and then the nitrogen and hydrogen react with each other and give you just ammonia. You convert that to just urea or something, just instantly on the field. So it can be just a very small plant and give you the right the fertilizer in there. So that's how people are thinking. So this electrochemical setup, right? Then the question is, right, what is a better catalyst to facilitate that reaction? So we are also trying to use density functional theory and a computational protocol to right find out the guiding principles so that we can um, we can set right we can pick a small subset from a large candidate structure. So
Okay.
that's our goal. So because this theoretical protocol work best in the sense that I have a right many candidate structures,
Mm.
and right, anyone can perform better. And now I need to just screen them. And if I am an experimentalist and want to screen them one by one by one, that's a very tough job,
Yeah.
right? So rather than doing that, let's use this simulation,
Formulations.
right, so that you can pick a subset or tell experimentalist, okay, right, don't just do this 1,000, only do this 10 or this 20, or just search along this line. So that's guiding principles will be coming from the experiments.
Wonderful. Okay, Kali bhai, thank you and all the best for your research and current group.
Thank you, thank you.
Okay, in the next part of this podcast, we'll talk about career in academia.